Yeah, hello. Can you hear me?
Yes.
All right,
So,
great. Let me share Keynote and play. I have a question. Can you see my mouse?
can you move it?
I am moving it.
Uh, it's not moving for me.
Okay, then that's good to know. All right, if everything's ready, then I'll begin.
Yes, please take it away.
Okay. Hello, everyone, and thank you. I'm excited to be here. I'm currently an intern at Tweak with the sole goal from Richard Eisenberg to try to improve GHC compile times. So this talk's going to be a little bit about the saga to do that, or at least the way I've gone about it. And yeah, we'll see what happens. All right, so if you're given this goal by Richard Eisenberg, it's going to be hard to know where to begin because if you look at the issue list on GHC, there's at least 170 open issues just for compiler performance, and GHC itself is well designed but rather complicated project. There's over 600 modules just in the compiler alone. One way to know where to begin is simply just to ask GHC. So this is a Tiki profile. It's a way to do low-level profiling. It's specified in the GHC user manual, and there's good information on the GitLab wiki. And what we're looking at here is on the right we have our names of functions in STG. On the left in the second column, I have allocations in bytes, and on the first column, I have entries. And I've just removed the head of this Tiki profile and then sorted it by allocations. And if you look at this, what you'll notice is that the insert call to data.intmap internal is absolutely hammered. It's one of the most entered functions when I compiled or when I generated this Tiki profile and compiled this module. And the functions that you see above it are actually from the pretty printers, but that's a whole nother story. All this is to say that if we have small changes in the way that we are using these int maps, it's likely that we might produce large general effects in the compiler performance. There's more reasons to believe this is the case. So there's a lot of comments on the issue list if you've spent time reading it in the last month, like I have, from Sebastian Graf, pointing out that there's interactions with the insert function and a certain test in the test case. And he finally narrows it down to the unique type interacting with the IntMap insert function uh, in these issues on the or comments on the issue list. So that's really the goal of, or the topic of this talk is why are int maps sensitive to the unique type in GHC? So, well, what is the unique type? Well, uniques in GHC are just a new type wrapper over integers, but they're slightly more complicated than that. They're actually integers, 64-bit integers on a 64-bit machine, where we reserve the top 8 bits for a character class. The character class in a unique is used throughout the compiler to segregate the different uniques for different things. So if you generate a unique for a type constructor, you get a different class. If you generate a unique for a type variable, you get a different class. And the only difference is going to be in those top 8 bits. Okay, so this is what that's going to look like semi-graphically. So your top 8 bits is your character mask, your bottom 56 bits is your unique payload. That's the actual unique stuff in the unique. Okay, all that is to say that there's just a decent amount of variation in the top 8 bits of uniques in GHC. Well, why is that a problem, right? On the face of it, that doesn't seem like it's going to be that problematic. But enter int maps. So int maps are big endian Patricia tries. What that means is they're binary trees. All data is held at the leaves of the tree, and then the path of the leaves are based on the bit string of the key. Lastly, and this is going to be important, they're compressed tries. All right, so this is going to be more easy to understand with an example. So imagine you're building a tree, one of these big endian Patricia tries from containers. And I'm just going to create one where the keys are 1, 2, 3, and 4, and all the elements are 0, and I'm not going to show any of the elements. You start with the root node. We'll check the most significant bit. I'm inserting here. We'll check the most significant bit of the bit string of 1. If we see a 0, we'll go left. If we see a 1 in the most significant bit, we go right. That's how you get the binary behavior. When we insert just based on an empty tree, we just create a leaf node, no problem. When we insert 2, when we insert 2, we get to the first node that we created after inserting 1, and then we'll split the tree based on only the bits that change. So what you see, and this is why it's a compressed trie, is that in the second node where you have 0, 0, those 0, zeros are shared between the bit strings of 1 and 2, right? 0, 0, 0, 1 and 0, 0, 1, 0. So rather than having to compare each bit individually and creating more comparisons down the length of the tree, you just compress and store that prefix that's shared between them and only split that prefix when you have to. So you get less comparisons on average. So then again, if we insert 3, we still have the 0, zeros in the prefix that are shared between 1, 2, and 3 in their bit strings. And you see we've split the 1, 0 and 1, 1 because we no longer have a shared prefix. And then we don't split the 0, 0 until we insert a 4, right? Because now we have 0, 0 or 0, 0, 1, 1 and 0, 1, 0, 0. So we only have a prefix that's shared that's 1 bit long. But so that's where the performance of these int maps really come from. That's where the algorithmic complexity of big O of min of NW comes from, because in the worst case, you'll be comparing every single bit in the bit string, right? And this is also where the performance of sequential keys comes from in IntMap. So if you insert a lot of sequential keys, you're maximizing all the operations on that prefix. You have less comparisons than you otherwise would, and you have nice performance. But remember that we store the top character mask and the top 8 bits of the unique type in GHC, and then we put those into int maps, right? So what we're doing is we're artificially limiting that prefix and then therefore maximizing comparisons in the int map. That seems like a problem. Well, is it a problem? So the first thing to try is swap the character mask to little Endian. So this is our old function to make a unique. What you see here is we basically OR the character mask with the bits after we shift the character mask 56 bits to the left. The new version of this simply shifts the unique payload 8 bits to the left and then ORs the character mask. So what that should do is maximize the prefix of the bit string, and then we should have less comparisons on average and so on and so forth. That's what this is, again, my little representation. So now the unique payloads in the top 56 bits and our character mask is in the bottom 8 bits. And this is a result of continuous integration compiler performance tests. And you see, well, it doesn't actually do a whole lot. We have 2 tests that have marginally improved by about 1%. Everything else is in noise, which I think is evidence that the uniques actually aren't interacting poorly with IntMaps. Okay, well, another thing we could do is we can mix the uniques. Well, what does that mean? This code comes from Sebastian Graf, and he links to this GIST. What we mean by mix is we're going to scramble the bits in the bit string of the unique. So we're just going to randomize them, but we're going to do it in a rather clever way so that we can encode them so that they'll be randomized. And then when we need them, we can decode them and get our payload back out and our character mask. And so all this is a tiny hashing function. K forward and K backward are the keys to encode and decode. And then the only change that we make to our make unique function is we inline a call to encode to scramble the uniques. And if you do this, well, you get some performance benefits. So we see around 2% for a few tests and a few more goods, which are just on the edge of past the tolerance for the continuous integration. But again, it's not the big win we were looking for, right? So then I think, so the next question then to ask is, well, how many comparisons are actually being made in practice? The Tiki profile is wonderful because it gives us this nice low level information, but it doesn't give us, it sums over it. It gives us the total number. It doesn't tell us, well, what's the distribution? So that's what we're going to do. I'm going to add a counter to count comparisons in insert and lookup in the IntMap internal containers module. Then I'm going to build a custom GHC with that insert and lookup or that containers. And then I'm going to generate data on size and comparison count when compiling various Haskell projects. And if you do this, you'll have to let your computer run for a while because it ends up being a lot of data. So I'm going to show you a lot of data now. Basically, the rest of the talk is data. And I need to orient you so you understand how to read some of these plots first. So this is the first test case, and it's kind of what you should consider as the baseline. So this is the IntMap benchmark suite. So I did my containers hack, and now I compiled the benchmark suites and ran it. What you see is on the left side is our insert function, on the right side is our lookup function. Notice also on the bottom plots, the y-axis is log base 10. That's always going to be log base 10. And the takeaway here is that on average, the benchmarks for IntMap do 5 comparisons for inserts. For lookups, there are always 13 comparisons. The reason there are always 13 comparisons is because the benchmarks suite in IntMap creates a tree that's 4,096 elements long, which ends up being 13 comparisons. That's also why if you look on the bottom right plot, the size of the IntMap is always 4096. Oh yeah, I also forgot. The top plots are the number of comparisons on the x-axis. The bottom plots are the size of the distribution of size of IntMaps during the analysis. So we get a distribution of comparisons and we get a distribution of size. These plots are a little more complicated. So these are empirical cumulative density function plots. And if you don't know how to read them, they can be kind of hard to read, but I'll walk through it here. So the reason I'm plotting these is because these kinds of plots are, they give nice information of, well, how much of my distribution is greater than some value. So if you look on this slide, we see that 5 is the mean in the top left plot of inserts. So on average, we do 5 comparisons. Well, I want to know how much of this distribution is above 5. You're going to say 50% because it's the mean. So if we look at the similar plot or another representation of the same data, that's in the middle to the left. And you see that you have this orange or red curve. You look at 5, on the x-axis of comparisons, draw that up, and you'll see on the y-axis, we're at 50%. So when you have a normal distribution in ECDF plot, you see this S-curve. Now I've also added black lines here that are important. So the x-axis on the top plot is the expected value that we would get for comparisons if we just had a self-balancing binary tree. So I take the size of the tree, I log base to it, and then take the ceiling of that. What that means then, and subtract that number from comparisons. What that means then is that if you see negative numbers on the top plot, the most of the distribution is on the negative side. That's good. That means we've done less comparisons than we normally would had we had a binary tree, a self-balancing binary tree. If you see positive numbers, that's bad. That means we've ended up doing more comparisons than we normally would with a self-balancing binary tree. And then for lookups on the right-hand side, it's not really good data because you just see everything's going to be at 13 and 1 because of the way the benchmarks work. The middle plots, the black line on 7, for the middle plots, the reason I marked this was because hashed array map tries, which are popular in the closure community, guarantee 7 comparisons. So if you look at the black line in the middle plots, follow that up to the ECDF curve, then you can calculate what percent of time would we just be better off using hashed array map tries. Okay, that was a lot of information. Let's start looking at some real data. So this is a module spectral simple main that we use in the NoFib benchmark suite that GHC has. It's just a normal kind of sandy check, but this is our first real data. So what you see is we have our on the top left for inserts, we're centered around 6 comparisons, but then we also have a spike at 13 and 14 for lookups. Similarly, lookups, most of our maps are either around less than 500 size or 500 elements, or they're at, for some reason, peaked at 3,600 around. This is what the ECDF plots look for this, and this is an example of what bad looks like. So you see at the top, most of the time, we're actually okay, where most of our distribution is as good as a balanced binary tree. But if you follow this, you see about 10% of the time, we're worse than a balanced binary tree. Same thing with lookups. About 15% of the time, we see positive numbers on the x-axis, so we're worse than a balanced binary tree. For comparisons, we're centered around, so if we compared this with hashed array map tries, it's about 20% of the time a hashed array map try when compiling this module would perform better. Similarly with lookups. So you follow the black line from 7 up to the blue line, and you go to the left, and it's about 20% of the time. Okay, but that's just a single module. What if we did this analysis with all of the performance tests in GHC? If you do that, then you get a power distribution where it's always centered around 0. What that means is that most of the time we're inserting and looking up into an empty map, which again is not very surprising because we're constantly compiling these small little files. But these are just, one-off comparisons. Most of the time when I'm compiling something or using GHC, I'm compiling packages. Oh, and then this is the ECDF. So you see the ECDF for the performance test, 100% of the distribution doesn't get to positive numbers on the top plots. That's the key takeaway here. Okay, so what if we compile packages like Pandoc? So if you compile Pandoc, and there was so much data here, I had to take a 55% sample because, well, R was starting to die. You'll find that the overwhelming majority of the time, we are inserting and looking up into maps that are relatively small. Remember that the size of these maps is in the bottom plots, and the y-axis there is log base 10. So changes there are really quite significant. And if you end up looking at this in more detail, and I'll make the data public, most of these maps end up being around 1,000 elements. Okay, so that's Pandoc. For the ECDF functions, we see that, again, about 20% of the time, looking at these middle plots, hashed array map tries would perform better because the 20% of the distribution is over 7 comparisons, and that's the maximum you would get with hashed array map tries. But using just a balancing binary tree, we're actually pretty okay. So at the top, if you look at the top plots, about 5% of the time on our inserts are worse, and about 15% of the time our lookups are worse when we're compiling Pandoc. Well, what about ASON? Oh, and I'll have to switch. I'm going to skip ASON for time because I want to get to the big one. What about Cobble? So Cobble took a much longer to run and is much worse. So I've overlaid quantiles here, and you can see that. So let's look at the top left plot. 95% of the time, so the 95% quantile when compiling Cobble, you have 9 comparisons for the insert. 99.9%, you have 18 comparisons. And so if we look at the size, 95% of this distribution is around 1,200 elements, but the 99.9% is 10,000. So what we have is when compiling Cobble, most of these int maps are less than 2,000 elements, around 1187, right? But it's just this long tail that's extremely long. So the question I want to ask then, or the conclusions of this rather long amount of data, is, are these really the right data structure to be using? If most of the time our data structures aren't getting longer or larger than 2,000 elements, then should we be even bothering using something like the Big Endian Patricia try? I think we definitely need to try the hashed array map tries or Bagwell tries. So Bagwell tries would even perform even better, but I don't think there's an implementation in Haskell. And then also the takeaway from this kind of data analysis is most of these operations are being dominated by empty trees. Why? The non-empty list has been in base for a while, and I almost wonder if there's some mapping function somewhere that's just inserting and then appending a bunch of empty trees. Okay, so that's a lot to say that I don't have the answers yet, but they're on their way. And I'm way over time. Apologies. If you would like, here's the references. You can follow me on Twitter. You can follow me on GitHub or GitLab. I'll make the data available, and I'm also on the GHC Dev and Haskell IRC if you want to talk about this. And that's what I have. Thank you.
Thank you so much. Wow, that was an awesome talk. I especially liked it because I remember writing the initial IntMap implementation when I read Andy Gill's and Chris Okasaki's paper.
Mhm.
This is already, I don't know, 20 years ago, right? So it's
Yeah.
very surprising to see these results. I think there was an interesting. Simon remarked that about the small. Why you see so many small ones there? Small maps dominate. That makes sense, not because programs are small, but because free var and occurrence analysis builds up sets from the leaves, right? I
I
believe
see.
that too, right? So I think optimizing for small ones would be really good. Can I? One initial question I had was you started out the talk by saying like, why is unique so impacting int maps? But then you kind of showed it wasn't little Endian or big Endian. Uh, but do you have? I don't think you actually answered the question, right?
Yeah. I think the answer to the question is that it's not actually impacting bitmaps or int maps. So up here, right? So the idea was that these prefixes, we end up with if the uniques were interacting poorly with the int maps, we would end up in a degenerate case like this, where we don't have large prefixes in our internal nodes, right? And so that was the motivation for the entire comparisons plots here. But the result of the analysis is really that in most of the time it's fine. It's like if we look at something that's realistic, like Pandoc, 5% of the time it's completely okay. So I think the takeaway isn't so much that the uniques are actually creating it, or the uniques are interacting poorly with int maps, and therefore on some modules we get these slowdowns or high allocations. I really think that the takeaway is that we could use something that has better higher bounds or has better performance if we know that the size of the container is less than 2,000 elements, right? I think these plots are too big to ignore, where you see, orders of magnitude difference in tree sizes from 0 to 500 elements. And maybe, if I'm not quite sure how to change the compiler to optimize for that, but it seems like something that should be optimized. Um, did I answer your question or the question of the
Yeah.
talk?
Yes. Yes.
Yeah, yeah,
I think what you're eventually suggesting is saying like maybe we should switch halfway. Like once the data structure
yeah,
becomes bigger than 1,000, we should maybe use
yeah,
another form, right?
yeah. I agree. Yeah, I think that's the next step forward.
So I think Sebastian Graf had an idea. You want to talk about that, Sebastian?
Yeah, yeah, I can talk a bit about it. So, yeah, well, I think you just answered my question basically. So, an idea would be to turn the unique FM, which is the map implementation that
Yeah,
maps uniques and uses an IntMap as the underlying map implementation. We could turn the unique FM into a hash array map trie or into a backwall trie. Not sure what that is, but at least I thought it was related to hash array map tries.
it is. It's an
Um,
improvement over it.
okay, cool.
Yeah,
Yeah, so at some fixed metric, like maybe 1,000 elements, or based on tree depth, which maybe measures more accurately whether or not the tree has or is degenerate.
hmm
Well,
yeah. So
just an idea.
no, that's a good idea. I actually have a branch up already that implements unique FM with the hash maps, which are hashed array map tries. But unfortunately, like all experiments worth doing, it went to the work in progress graveyard, which is GHC panic and the liveness analysis of register
Ah, yes.
allocation. Yeah, and I still have to. I was racing to try to get something yesterday, and I just gave up around last night. So curiously, though, I can still build the stage one compiler, so I can still check allocations on the stage one compiler compared to master, and I'll probably do that today, because my day's just starting.
Cool.
Yeah, to see if there's a difference.
Yeah, sounds great. I think you are really into this, and it's great that somebody is going to tackle this, because I think the myths that are building up around, or that we seem to create around IntMaps and uniques and so on, they just keep getting more annoying. And yeah, it's good that somebody takes the time to clear it all up.
Yeah.
So
yeah,
thanks.
I was enticed by Richard's low-hanging fruit, and then it turned out to be anything but low-hanging fruit.
Yeah.
Right. So I think let's thank the speaker.
And I will
Very
stop
interesting.
sharing.
So the next talk is a lightning talk about pinned warnings by